Hello and welcome to today's lesson on understanding the equation E equals QV. Today we will start by exploring the intuition behind the relationship between electrical charge and energy transfer. Next, we'll introduce the equation E equals QV and look at some examples. So far, we have discussed the basics of circuits, including key concepts like resistance, voltage, and current. You are already familiar with how these fundamental elements interact within an electrical circuit to produce a desired outcome. When an electrical charge flows through a circuit, it encounters resistance, causing electrons to collide with atoms in the material. These collisions convert the energy of the electrons into heat or other forms of energy. If more electrons are involved, there are more collisions, and thus more energy is transferred to the material. This means that as the charge Q increases, the energy transferred, E, also increases. Moreover, the strength of these collisions is influenced by the potential difference or voltage. A higher voltage means a stronger push on the electrons, leading to more energetic collisions. Hence, as voltage increases, the energy transferred also increases. Therefore, we would expect energy transferred depends directly on both charge and voltage. The equation for energy transferred in an electrical circuit is given by E equals QV. Here, E stands for energy transferred in joules, Q represents the charge in coulombs, and V is the potential difference in volts. This formula aligns perfectly with our intuition. As either the charge or the voltage increases, the energy transferred increases proportionally. Let's consider an example to solidify this understanding. Imagine you have a small circuit with a voltage supply of 5 volts and 2 coulombs of charge passing through. Using the formula E equals QV and plugging in the values, we can calculate the energy transferred as E equals 2 times 5. This gives you that the energy is equal to 10 joules. So, in this scenario, 10 joules of energy are transferred to the circuit. This example illustrates how the equation E equals QV allows us to quantify the energy transfer based on the electrical charge and voltage in the circuit. Let's try a few more examples. Suppose you have a circuit with a power supply of 8 volts and 3 coulombs of charge passing through. How would you calculate the energy transferred? Using E equals QV and plugging in Q equals 3 coulombs and V equals 8 volts, we obtain that the energy equals 8 times 3, so 24 joules. Let's try another question. In a circuit with a power supply of 10 volts, 15 joules of energy are transferred in a given time. We want to work out how many coulombs of charge pass through the circuit during that time interval. To answer this, we can rearrange the equation E equals QV for Q. This gives us Q equals E divided by V. Now plug in the values E equals 15 joules and V equals 10 volts to obtain Q equals 15 divided by 10, so Q equals 1.5 coulombs. Let's try one final question. Suppose you have a circuit with a power supply of 12 volts and a current of 2 amps passing through. We want to work out the energy transferred in 4 seconds. Since we want to work out energy, it would make sense to use E equals QV. The issue here is that while we are given the value of V, we are not directly given the value of Q. Remember from previous lessons, though, that we have a formula for calculating charge, that is Q equals IT. Plugging in the values for I and T gives Q equals 2 times 4, which equals 8 coulombs. We can then plug this number into E equals QV to obtain E equals 8 times 12, so 96 joules. In today's lesson, we delved into the equation E equals Q times 5 and its significance in the context of energy transfers in everyday appliances. By understanding this equation, we can calculate the energy transferred when an electric charge moves through an appliance. In our next lesson, we'll further our understanding and use this equation to look at power in electric circuits.